So in the last video, we learned that light is going to both reflect and transmit at a particular boundary. So let's do this. Let me just draw a boundary. So this is going to be medium 1 and this is going to be medium 2. Doesn't actually really matter how I call those. This could be 1, this could be 2. But I'm going to let a ray of light be incident upon this boundary. So like I said, a portion of that light is going to be reflected. I'll do that in the same color. And a portion is going to be transmitted. I'll do that in a different color. And I've tried to draw it such that the angle has shifted slightly from our transmission. Okay, so we have two cases. On this boundary between media, the light, part of the light reflects, part of it transmits. To really be able to characterize this, what we need to do first is construct a line normal to the surface. Remember, normal is just a fancy word for perpendicular. But as soon as I do that, I now have a tool to use to calculate angles. We're going to be using angles a lot in the study of geometric optics. That might not be a surprise if you hear the word geometric. So let's label some things. I'm going to call this angle theta sub I for theta incident, right? Notice that I'm measuring it from the normal line. Normal to what? Normal to the incident surface. The surface on which it's incident, I should say. So here's theta incident. Okay, well that means this angle is theta, and I will say R for reflected. So theta incident, theta reflected. Let me take care of the other case too. This angle, with respect to the normal, is the angle of transmission. I'm going to actually subscript this one, not with a T, but with an RF for the word refracted. Reflection and refracted sound really similar, so let's not get them confused. This is theta reflected, this is theta refracted. We'll talk about that word in just a second. So I need to be able to characterize both cases. Let's take care of the easy one first. Let me introduce you to the law of reflection, which is probably, quite possibly, the easiest physical law you're ever going to encounter. So, law of reflection just says this: theta incident is equal to theta reflected every time. This is actually never violated, although it seems to be sometimes. But if I have a nice smooth surface like this, you can think of this as a mirror or maybe a really still body of water. It's really easy to see that theta reflected is the same angle. I'm going to come back to this sheet. Let's talk about two different types of reflection we can get. First we'll see exactly what I just drew. Here's my boundary. Notice I've drawn it nice and smooth. And let me just draw a couple of incident rays. I'm going to let them all come in parallel. They don't have to, but I'm going to let them come in basically parallel. And then I'm going to notice that they are going to leave parallel. If they're all coming in at the same angle and all being reflected at the same angle, I will find that whatever orientation they're in, parallel or not, they're going to be in the same orientation as they are reflected. We call this type of reflection specular reflection. This is the sort that you see in the mirror, and this forms images, right? There's an image of you formed in the mirror. So that's specular reflection. However, if I have a surface that's not so smooth, which any surface is not smooth if you look close enough, let's say I have a surface that's kind of jagged. Well, light comes in and it obeys the law of reflection. The problem is that now if I'm going to calculate a normal line to this surface, I've got to calculate different normal lines all over the place. If I let a ray of light come in, we get a different color. Thusly, it looks to me like the normal to the surface is about there, and so this thing is going to actually, looks like to me it's going to exit that way. And then let another ray come in over here. It looks to me like that one's going to reflect thusly, but then it hits this and reflects thusly. And so let me let another one come in over here. And it looks like that's going to reflect here and then here. So you see what's happening. These rays, which I have drawn parallel at first, are now all cattywampus. They've been moved around. I don't get a good image out of this. If my mirror is really, really rough, I don't get a good image. We call this diffuse reflection. And I should point out, this is how you see everything that you see, basically. If you look down at your shirt is some color. I don't know what color it is. Mine's gray. But I look down at my shirt and it's gray. How do I know it's gray? Because light is striking my shirt and it's bouncing off of my shirt. And some of that light is then entering my eyeballs. And I can see that it's gray. Now, is an image formed in my shirt? No, I don't look at my shirt in the morning to make sure that everything's, you know, I've washed my face or everything. I don't see myself in my shirt, but I do see my shirt. That is diffuse reflection. I see my shirt by the action of the light bouncing off of it, but I don't see an image. For specular reflection, I do see an image. Interestingly enough, sometimes diffuse reflection kind of bleeds over into specular reflection. If you've ever been driving on a highway after a rainstorm, rainwater will fill in these little gaps and it will make somewhat of a smooth surface, and you can actually see images of cars. You can see reflections of cars in the roadway, especially if they have their lights on, because the water will fill in these gaps and you get something approaching specular reflection. Or if you've ever been out on a very calm lake and it's really, really crystal clear because there's no wind, you can see gorgeous reflections in the water. But then if a little wind comes along, it ripples the water and those reflections distort. So you get specular reflection kind of bleeding over into diffuse reflection. Those are the two kinds of reflection that we can get. Now, let's go back here and talk about what happens to the transmitted portion of this ray. Well, to do that, I'm going to have to introduce you to a concept. Well, I'm going to come back to this sheet again. Let's do some more side work. In fact, let's just go back to this sheet because we have more space. Let me introduce you to a really, really special number. We symbolize it with the letter C. If you've ever seen Einstein's famous equation, E equals mc squared, that's this C. This is the speed of light. It is equal to about 2.99 times 10 to the 8th meters per second, something really, really fast. There's some more decimal places. You can look that up if you're interested. But this is the speed of light, and I should say this, in vacuum. As it turns out, it's basically the speed of light in air also. We're gonna, for all practical purposes, the speed of light in air is the same as the speed in vacuum. It slows down a little bit, but we're gonna consider this to be in vacuum or in air. The point is, this is the fastest that light is ever gonna travel. As it turns out, as it enters a new medium like glass or water or diamond, something like that, it slows down in every case. Air and vacuum represent the fastest light is ever going to travel, but if it enters another medium, it will actually slow down. We can characterize that by coming up with an index of refraction. N, the index of refraction, it's going to be defined as the speed of light in vacuum divided by the speed of light in the new medium. So N is material specific. What I'm saying is the index of refraction of water is the index of refraction of water. It's different than the index of refraction of, say, glass, but there is an index of refraction of glass. Okay, so whatever this index of refraction is will depend upon your substance, depend upon your medium. Let's think about this for a little bit. If C is the fastest this is ever going to go, that means the denominator is always going to be, the numerator is always going to be bigger than the denominator, right? If it always slows down, if V in the medium is always slower than V in C in vacuum, then the denominator here is always going to be less than the numerator. What that means, N is always greater than or equal to 1. It is dimensionless. You've got meters per second up here, meters per second down here. They're going to cancel. But the lowest N will ever be is 1. It's going to be 1 in air and in vacuum. In every other substance, it's going to be bigger than 1. Usually it's only slightly bigger. Diamond has an index of refraction of I think it's about 2.14, which is pretty high. But between this and 1 and 2.14 is a lot of numbers, right? So different media will have different indices of refraction. All right, so notice also what this means. Because we said that N is greater than or equal to 1, because the speed in the medium has something to do with N, the slower it goes, the smaller the denominator, the bigger the index of refraction. So I'll say this, the greater N, the slower speed. The bigger N is, the slower the speed is. So if you have an index of refraction of, say, 3, I don't know of any material with that high of an index of refraction, but if some existed, that means light has slowed down pretty significantly as it enters into that medium. If you have an index of refraction of 1.001, that means light is only slowed down just a little bit as it enters that medium. Okay, so that's the index of refraction. Now, finally ready to go back to the first page here. To characterize this angle and how light behaves as it moves into a new medium, let's introduce you to the law of refraction. Which says this: N1 sine theta 1 is equal to N2 sine theta 2, where 1 and 2 are just placeholders for one of the media. This actually works both ways. It doesn't really matter. If I'm coming from, in this case, 1 to 2, I would just put whatever index of refraction in this material here. Sine of theta 1 is that, in that case, this theta incident. And then N2 would be whatever index of refraction is in this material. Theta 2 would be the the angle of refraction, this theta refracted. It's an equivalence, so it works both ways. It's not a big deal. But we get really interesting results if we look at some different cases. So this is the law of refraction, sometimes called Snell's law, but I usually stick with law of refraction. Let's look at some different cases and see what we can come up with. So let me take this and let me just rearrange a couple things. Do some cross multiplying and dividing. I'm going to get all the n's on one side. N1 over N2, just divided through by N2, is equal to sine theta 2 over sine theta 1. Right, I got all the signs together. I got all the n's together. So I have three different possibilities. The first possibility is that N1 is equal to N2. and I get 1, that's a very boring case. I get 1 out of this fraction and 1 out of this fraction. It's a boring case because that means I didn't actually change media, right? I just had the same index of refraction twice. So that's kind of a boring case. We're not going to look at that one. But case 1 is this. N1 over N2 is greater than 1. Right? Anytime I have a fraction, that could be the case. It could be less than 1, it could be 1, it could be greater than 1. I've already said that 1 is uninteresting. But what about this case? N1 over N2 is bigger than 1. That means the numerator's bigger. What that means is that on the right side, the numerator's bigger. That means sine theta 2 is bigger than sine theta 1. Right? Which also means, because these are both sines, theta 2 is bigger than theta 1. That's actually the opposite of what I've drawn here. So let me draw that case. So I have 2 different cases here. What I've drawn with the blue arrow is the refracted angle. Theta refracted is less than theta incident. In this case, theta refracted is bigger than theta incident. Now, what I'm also doing is I'm using the numbers I've given up here as 1 and 2 to 1 and 2 here. So theta 1 is the angle up here, theta 2 is the angle down here. Okay, what does that mean? Well, it means, to use the right terms, that the light has bent away from the normal. Look, if I were to draw in the original path of this light, that is to say the path that light would take if no boundary were in its way, this angle that I've gotten from this case has bent away from the normal with respect to that line. The other one has bent towards the normal. But in this case, I've bent away from the normal. Now, what does that mean here? Well, what I've said is that N1 is bigger than N2. And if that's the case, I get this bending away from the normal. What does it mean for N1 to be bigger than N2? Well, remember, the bigger the index of refraction, the slower light is moving. So what that means is that if this is true, light is moving more slowly in this medium than it is in this medium. Light has sped up as it leaves medium 1. So it's coming here, it's traveling slower, it gets into this medium, it speeds up. If that happens, if the light speeds up, I see it bending away from the normal. And I just got that out of looking at Snell's law, or the law of refraction. Let me move this up and look at the next case, which is, of course, the case where N1 over N2 is less than 1, which is going to imply that sine theta 2 is less than sine theta 1, which also implies that theta 2 is less than theta 1. The angles will go as the sines. So, what does this mean? Well, if theta 2 is less than theta 1, that is the original case I drew up here in blue. That means the light has bent towards the normal. Okay, well, what happened here? If N1 is bigger than N2, what this means is that if N1 over N2 is less than 1, that means N1 is smaller than N2. And the index of refraction, the smaller it is, the faster light's moving. So this represents the case where the light moves faster in this first medium than in the second medium. So if that's the case, if the light slows down, I see it bending towards the normal. Let me write that out, both of those things. When moving from medium 1 to medium 2, if light slows down, it bends towards the normal. If light speeds up, again, moving from medium 1 to medium 2, speeds up, it bends away from the normal. Notice this case, light slowing down, that covers every single case in which light enters a new medium from the air. Because what we said is in air and in vacuum, light is going the fastest it will ever go. So anytime light is incident upon a surface and transmits into the new medium from air, it will bend towards the normal. Likewise, anytime light is incident from some other substance and passes into air or vacuum, it will bend away from the normal as it moves into its new medium. With other media, you just have to compare their indices of refraction. All right, so that is the law of refraction. In the next video, we're going to look at a really interesting effect that comes out of the law of refraction.